A microphone is an acoustic-to-electric transducer or sensor that converts sound in air into an electrical signal. Microphones are used in many applications such as telephones, hearing aids, public address systems for concert halls and public events, motion picture production, live and recorded audio engineering, two-way radios, megaphones, radio and television broadcasting, and in computers for recording voice, speech recognition, VoIP, and for non-acoustic purposes such as ultrasonic checking or knock sensors. Most microphones today use electromagnetic induction, capacitance change or piezoelectricity to produce an electrical signal from air pressure variations. Microphones typically need to be connected to a preamplifier before the signal can be amplified with an audio power amplifier or recorded. History: in order to speak to larger groups of people, there was a desire to increase the volume of the spoken word. The earliest known device to achieve this dates to 600 BC with the invention of masks with specially designed mouth openings that acoustically augmented the voice in amphitheaters. In 1665, the English physicist Robert Hooke was the first to experiment with a medium other than air with the invention of the lover's telephone made of stretched wire with a cup attached at each end. German inventor Johann Philipp Reis designed an early sound transmitter that used a metallic strip attached to a vibrating membrane that would produce intermittent current. Better results were achieved with the liquid transmitter design in Scottish-American Alexander Graham Bell's telephone of 1876. The diaphragm was attached to a conductive rod in an acid solution. These systems, however, gave a very poor sound quality. Carbon microphone. The first microphone that enabled proper voice telephony was the carbon microphone. This was independently developed by David Edward Hughes in England and Emil Berliner and Thomas Edison in the US. Although Edison was awarded the first patent in mid-1877, Hughes had demonstrated his working device in front of many witnesses some years earlier, and most historians credit him with its invention. Hughes' device used loosely packed carbon granules. The varying pressure exerted on the granules by the diaphragm from the acoustic waves caused the resistance of the carbon to vary proportionally, allowing a relatively accurate electrical reproduction of the sound signal. Hughes also coined the word microphone. He demonstrated his apparatus to the Royal Society by magnifying the sound of insects scratching through a sound box. Contrary to Edison, Hughes decided not to take out a patent. Instead he gave his invention as a gift to the world. The carbon microphone is the direct prototype of today's microphones and was critical in the development of telephony, broadcasting and the recording industries. Thomas Edison refined the carbon microphone into his carbon button transmitter of 1886. This microphone was employed at the first ever radio broadcast, a performance at the New York Metropolitan Opera House in 1910. Further developments: in 1916, C. Wendt of Bell Labs developed the next breakthrough with the first condenser microphone. In 1923 the first practical moving coil microphone was built. The Marconi Skyx, or magnetophone, developed by Captain H. J. Round, was the standard for BBC studios in London. This was improved in 1930 by Blumnin and Holman, who released the HB1A and was the best standard of the day. In the same year, the ribbon microphone was introduced, another electromagnetic type, believed to have been developed by Harry F. Olson, who essentially reverse-engineered a ribbon speaker. Over the years these microphones were developed by several companies, most notably RCA, that made large advancements in pattern control, to give the microphone directionality. With television and film technology booming, there was demand for high-fidelity microphones and greater directionality. Electro Voice responded with their Academy Award-winning shotgun microphone in 1963. During the second half of 20th century, development advanced quickly, with the Shaw brothers bringing out the SM58 and SM57. Digital was pioneered by Marleb in 1999 with the DM1001. The latest research developments include the use of fiber optics, lasers and interferometers. Components: the sensitive transducer element of a microphone is called its element or capsule. Except in thermophone-based microphones, sound is first converted to mechanical motion by means of a diaphragm, the motion of which is then converted to an electrical signal. A complete microphone also includes a housing, some means of bringing the signal from the element to other equipment, and often an electronic circuit to adapt the output of the capsule to the equipment being driven. A wireless microphone contains a radio transmitter. Varieties: microphones are referred to by their transducer principle, such as condenser, dynamic, etc., and by their directional characteristics. Sometimes other characteristics such as diaphragm size, intended use or orientation of the principal sound input to the principal axis of the microphone are used to describe the microphone. Condenser microphone. The condenser microphone, invented at Bell Labs in 1916 by E.C. Wendt, is also called a capacitor microphone or electrostatic microphone. Capacitors were historically called condensers. Here, the diaphragm acts as one plate of a capacitor, and the vibrations produce changes in the distance between the plates. There are two types, depending on the method of extracting the audio signal from the transducer: DC-biased microphones, and radio frequency or high-frequency condenser microphones. With a DC-biased microphone, the plates are biased with a fixed charge. The voltage maintained across the capacitor plates changes with the vibrations in the air, according to the capacitance equation, where Q equals charge in coulombs, C equals capacitance in farads, and V equals potential difference in volts. The capacitance of the plates is inversely proportional to the distance between them for a parallel plate capacitor. The assembly of fixed and movable plates is called an element, or capsule. A nearly constant charge is maintained on the capacitor. As the capacitance changes, the charge across the capacitor does change very slightly, but at audible frequencies it is sensibly constant. The capacitance of the capsule and the value of the bias resistor form a filter that is high pass for the audio signal, and low pass for the bias voltage. Note that the time constant of an RC circuit equals the product of the resistance and capacitance. Within the time frame of the capacitance change, the charge is practically constant and the voltage across the capacitor changes instantaneously to reflect the change in capacitance. The voltage across the capacitor varies above and below the bias voltage. The voltage difference between the bias and the capacitor is seen across the series resistor. The voltage across the resistor is amplified for performance or recording. In most cases, the electronics in the microphone itself contribute no voltage gain, as the voltage differential is quite significant, up to several volts for high sound levels. Since this is a very high impedance circuit, current gain only is usually needed, with the voltage remaining constant. RF condenser microphones use a comparatively low RF voltage, generated by a low-noise oscillator. The signal from the oscillator may either be amplitude modulated by the capacitance changes produced by the sound waves moving the capsule diaphragm, or the capsule may be part of a resonant circuit that modulates the frequency of the oscillator signal. Demodulation yields a low-noise audio frequency signal with a very low source impedance. The absence of a high bias voltage permits the use of a diaphragm with looser tension, which may be used to achieve wider frequency response due to higher compliance. The RF biasing process results in a lower electrical impedance capsule, a useful byproduct of which is that RF condenser microphones can be operated in damp weather conditions that could create problems in DC-biased microphones with contaminated insulating surfaces. The Sennheiser MKH series of microphones use the RF biasing technique. Condenser microphones span the range from telephone transmitters through inexpensive karaoke microphones to high-fidelity recording microphones. They generally produce a high-quality audio signal and are now the popular choice in laboratory and recording studio applications. The inherent suitability of this technology is due to the very small mass that must be moved by the incident sound wave, unlike other microphone types that require the sound wave to do more work. They require a power source, provided either via microphone inputs on equipment as phantom power or from a small battery. Power is necessary for establishing the capacitor plate voltage, and is also needed to power the microphone electronics. Condenser microphones are also available with two diaphragms that can be electrically connected to provide a range of polar patterns, such as cardioid, omnidirectional, and figure-8. It is also possible to vary the pattern continuously with some microphones, for example Arada Northwest Territories, 2000 or CAD M179. A valve microphone is a condenser microphone that uses a vacuum tube amplifier. They remain popular with enthusiasts of tube sound. Electret condenser microphone. An Electret microphone is a type of capacitor microphone invented by Gerard Sessler and Jim West at Bell Laboratories in 1962. The externally applied charge described above under condenser microphones is replaced by a permanent charge in an Electret material. An Electret is a ferroelectric material that has been permanently electrically charged or polarized. The name comes from electrostatic and magnet. A static charge is embedded in an Electret by alignment of the static charges in the material, much the way a magnet is made by aligning the magnetic domains in a piece of iron. Due to their good performance and ease of manufacture, hence low cost, the vast majority of microphones made today are Electret microphones. A semiconductor manufacturer estimates annual production at over 1 billion units. Nearly all cell phone, computer, PDA and headset microphones are Electret types. They are used in many applications, from high-quality recording and lavalier used to built-in microphones in small sound recording devices and telephones. Though Electret microphones were once considered low quality, the best ones can now rival traditional condenser microphones in every respect and can even offer the long-term stability and ultra-flat response needed for a measurement microphone. Unlike other capacitor microphones, they require no polarizing voltage, but often contain an integrated preamplifier that does require power. This preamplifier is frequently phantom-powered in sound reinforcement and studio applications. Monophonic microphones designed for personal computer use, sometimes called multimedia microphones, use a 3.5 and plug is usually used, without power, for stereo. The ring, instead of carrying the signal for a second channel, carries power via a resistor from a 5V supply in the computer. Stereophonic microphones use the same connector. There is no obvious way to determine which standard is used by equipment and microphones. Only the best Electret microphones rival good DC polarized units in terms of noise level and quality. Electret microphones lend themselves to inexpensive mass production, while inherently expensive non-Electret condenser microphones are made to higher quality. Dynamic microphone. Dynamic microphones work via electromagnetic induction. They are robust, relatively inexpensive and resistant to moisture. This, coupled with their potentially high gain before feedback, makes them ideal for on-stage use. Moving coil microphones use the same dynamic principle as in a loudspeaker, only reversed. A small movable induction coil, positioned in the magnetic field of a permanent magnet, is attached to the diaphragm. When sound enters through the windscreen of the microphone, the sound wave moves the diaphragm. When the diaphragm vibrates, the coil moves in the magnetic field, producing a varying current in the coil through electromagnetic induction. A single dynamic membrane does not respond linearly to all audio frequencies. Some microphones for this reason utilize multiple membranes for the different parts of the audio spectrum and then combine the resulting signals. Combining the multiple signals correctly is difficult and designs that do this are rare and tend to be expensive. There are on the other hand several designs that are more specifically aimed towards isolated parts of the audio spectrum. The AKG D112, for example, is designed for bass response rather than treble. In audio engineering, several kinds of microphones are often used at the same time to get the best result. Ribbon microphone. Ribbon microphones use a thin, usually corrugated metal ribbon suspended in a magnetic field. The ribbon is electrically connected to the microphone's output, and its vibration within the magnetic field generates the electrical signal. Ribbon microphones are similar to moving coil microphones in the sense that both produce sound by means of magnetic induction. Basic ribbon microphones detect sound in a bidirectional pattern because the ribbon, which is opening to sound both front and back, responds to the pressure gradient rather than the sound pressure. Though the symmetrical front and rear pickup can be a nuisance in normal stereo recording, the high side rejection can be used to advantage by positioning a ribbon microphone horizontally, for example above cymbals, so that the rear lobe picks up only sound from the cymbals. Crossed figure 8, or Blumlein pair, stereo recording is gaining in popularity, and the figure-8 response of a ribbon microphone is ideal for that application. Other directional patterns are produced by enclosing one side of the ribbon in an acoustic trap or baffle, allowing sound to reach only one side. The classic RCA Type 77DX microphone has several externally adjustable positions of the internal baffle, allowing the selection of several response patterns ranging from figure-8 to unidirectional. Such older ribbon microphones, some of which still provide high-quality sound reproduction, were once valued for this reason, but a good low-frequency response could only be obtained when the ribbon was suspended very loosely, which made them relatively fragile. Modern ribbon materials, including new nanomaterials, have now been introduced that eliminate those concerns, and even improve the effective dynamic range of ribbon microphones at low frequencies. Protective windscreens can reduce the danger of damaging a vintage ribbon, and also reduce plosive artifacts in the recording. Properly designed windscreens produce negligible treble attenuation. In common with other classes of dynamic microphone, ribbon microphones don't require phantom power. In fact, this voltage can damage some older ribbon microphones. Some new modern ribbon microphone designs incorporate a preamplifier and, therefore, do require phantom power, and circuits of modern passive ribbon microphones, that is, those without the aforementioned preamplifier, are specifically designed to resist damage to the ribbon and transformer by phantom power. Also, there are new ribbon materials available that are immune to wind blasts and phantom power. Carbon microphone. A carbon microphone, also known as a carbon button microphone, uses a capsule or button containing carbon granules pressed between two metal plates like the Berliner and Edison microphones. A voltage is applied across the metal plates, causing a small current to flow through the carbon. One of the plates, the diaphragm, vibrates in sympathy with incident sound waves, applying a varying pressure to the carbon. The changing pressure deforms the granules, causing the contact area between each pair of adjacent granules to change, and this causes the electrical resistance of the mass of granules to change. The changes in resistance cause a corresponding change in the current flowing through the microphone, producing the electrical signal. Carbon microphones were once commonly used in telephones. They have extremely low-quality sound reproduction and a very limited frequency response range, but are very robust devices. The Baudet microphone, which used relatively large carbon balls, was similar to the granule carbon button microphones. Unlike other microphone types, the carbon microphone can also be used as a type of amplifier, using a small amount of sound energy to control a larger amount of electrical energy. Carbon microphones found use as early telephone repeaters, making long-distance phone calls possible in the era before vacuum tubes. These repeaters worked by mechanically coupling a magnetic telephone receiver to a carbon microphone. The faint signal from the receiver was transferred to the microphone, with a resulting stronger electrical signal to send down the line. One illustration of this amplifier effect was the oscillation caused by feedback, resulting in an audible squeal from the old candlestick telephone if its earphone was placed near the carbon microphone. Piezoelectric microphone, a crystal microphone or piezo microphone, uses the phenomenon of piezoelectricity, the ability of some materials to produce a voltage when subjected to pressure, to convert vibrations into an electrical signal. An example of this is potassium sodium tartrate, which is a piezoelectric crystal that works as a transducer, both as a microphone and as a slimline loudspeaker component. Crystal microphones were once commonly supplied with vacuum tube equipment, such as domestic tape recorders. Their high output impedance matched the high input impedance of the vacuum tube input stage well. They were difficult to match to early transistor equipment, and were quickly supplanted by dynamic microphones for a time, and later small Electret condenser devices. The high impedance of the crystal microphone made it very susceptible to handling noise, both from the microphone itself and from the connecting cable. Piezoelectric transducers are often used as contact microphones to amplify sound from acoustic musical instruments, to sense drum hits, for triggering electronic samples, and to record sound in challenging environments, such as underwater under high pressure. Saddle-mounted pickups on acoustic guitars are generally piezoelectric devices that contact the strings passing over the saddle. This type of microphone is different from magnetic coil pickups commonly visible on typical electric guitars, which use magnetic induction, rather than mechanical coupling, to pick up vibration. Fiber-optic microphone. A fiber-optic microphone converts acoustic waves into electrical signals by sensing changes in light intensity, instead of sensing changes in capacitance or magnetic fields as with conventional microphones. During operation, light from a laser source travels through an optical fiber to illuminate the surface of a reflective diaphragm. Sound vibrations of the diaphragm modulate the intensity of light reflecting off the diaphragm in a specific direction. The modulated light is then transmitted over a second optical fiber to a photodetector, which transforms the intensity-modulated light into analog or digital audio for transmission or recording. Fiber-optic microphones possess high dynamic and frequency range, similar to the best high-fidelity conventional microphones. Fiber-optic microphones do not react to or influence any electrical, magnetic, electrostatic or radioactive fields. The fiber-optic microphone design is therefore ideal for use in areas where conventional microphones are ineffective or dangerous, such as inside industrial turbines or in magnetic resonance imaging equipment environments. Fiber-optic microphones are robust, resistant to environmental changes in heat and moisture, and can be produced for any directionality or impedance matching. The distance between the microphone's light source and its photodetector may be up to several kilometers without need for any preamplifier or other electrical device, making fiber-optic microphones suitable for industrial and surveillance acoustic monitoring. Fiber-optic microphones are used in very specific application areas such as for infrasound monitoring and noise cancelling. They have proven especially useful in medical applications, such as allowing radiologists, staff and patients within the powerful and noisy magnetic field to converse normally, inside the MRI suites as well as in remote control rooms. Other uses include industrial equipment monitoring and sensing, audio calibration and measurement, high-fidelity recording and law enforcement. Laser microphone. Laser microphones are often portrayed in movies as spy gadgets, because they can be used to pick up sound at a distance from the microphone equipment. A laser beam is aimed at the surface of a window or other plane surface that is affected by sound. The vibrations of this surface change the angle at which the beam is reflected, and the motion of the laser spot from the returning beam is detected and converted to an audio signal. In a more robust and expensive implementation, the returned light is split and fed to an interferometer, which detects movement of the surface by changes in the optical path length of the reflected beam. The former implementation is a tabletop experiment. The latter requires an extremely stable laser and precise optics. A new type of laser microphone is a device that uses a laser beam and smoke or vapor to detect sound vibrations in free air. On August 25, 2009, U.S. Patent 7,580,533 issued for a particulate flow detection microphone based on a laser photocell pair with a moving stream of smoke or vapor in the laser beam's path. Sound pressure waves cause disturbances in the smoke that in turn cause variations in the amount of laser light reaching the photodetector. A prototype of the device was demonstrated at the 127th Audio Engineering Society Convention in New York City from 9 through October 12, 2009. Liquid microphone. Early microphones did not produce intelligible speech, until Alexander Graham Bell made improvements including a variable resistance microphone transmitter. Bell's liquid transmitter consisted of a metal cup filled with water with a small amount of sulfuric acid added. A sound wave caused the diaphragm to move, forcing a needle to move up and down in the water. The electrical resistance between the wire and the cup was then inversely proportional to the size of the water meniscus around the submerged needle. Elisha Gray filed a caveat for a version using a brass rod instead of the needle. Other minor variations and improvements were made to the liquid microphone by Major Runner, Chambers, Banney, Sykes, and Elisha Gray, and one version was patented by Reginald Fessenden in 1903. These were the first working microphones, but they were not practical for commercial application. The famous first phone conversation between Bell and Watson took place using a liquid microphone. MEMS microphone. The MEMS microphone is also called a microphone chip or silicon microphone. The pressure-sensitive diaphragm is etched directly into a silicon chip by MEMS techniques, and is usually accompanied with integrated preamplifier. Most MEMS microphones are variants of the condenser microphone design. Often MEMS microphones have built-in analog-to-digital converter circuits on the same CMOS chip, making the chip a digital microphone and so more readily integrated with modern digital products. Major manufacturers producing MEMS silicon microphones are Wolfson Microelectronics, Analog Devices, Acoustica, Infineon, Knowles Electronics, Memstech, NXP Semiconductors, Sony and MEMS, AAC Acoustic Technologies, and Omron. Speakers as microphones. A loudspeaker, a transducer that turns an electrical signal into sound waves, is the functional opposite of a microphone. Since a conventional speaker is constructed much like a dynamic microphone, speakers can actually work in reverse as microphones. The result, though, is a microphone with poor quality, limited frequency response, and poor sensitivity. In practical use, speakers are sometimes used as microphones in applications where high quality and sensitivity are not needed, such as intercoms, walkie-talkies or video game voice chat peripherals, or when conventional microphones are in short supply. However, there is at least one other practical application of this principle, using a medium-size woofer placed closely in front of a kick in a drum set to act as a microphone. The use of relatively large speakers to transduce low-frequency sound sources, especially in music production, is becoming fairly common. A product example of this type of device is the Yamaha Sub King, a 6.5-inch woofer shock mounted into a 10-inch drum shell used in front of kick drums. Since a relatively massive membrane is unable to transduce high frequencies, placing a speaker in front of a kick drum is often ideal for reducing cymbal and snare bleed into the kick drum sound. Less commonly, microphones themselves can be used as speakers, almost always as tweakers. Microphones, however, are not designed to handle the power that speaker components are routinely required to cope with. One instance of such an application was the STC microphone-derived 4001 Super Tweaker, which was successfully used in a number of high-quality loudspeaker systems from the late 1960s to the mid-70s. Capsule design and directivity. The inner elements of a microphone are the primary source of differences in directivity. A pressure microphone uses a diaphragm between a fixed internal volume of air and the environment, and responds uniformly to pressure from all directions, so it is said to be omnidirectional. A pressure gradient microphone uses a diaphragm that is at least partially open on both sides. The pressure difference between the two sides produces its directional characteristics. Other elements such as the external shape of the microphone and external devices such as interference tubes can also alter a microphone's directional response. A pure pressure gradient microphone is equally sensitive to sounds arriving from front or back, but insensitive to sounds arriving from the side because sound arriving at the front and back at the same time creates no gradient between the two. The characteristic directional pattern of a pure pressure gradient microphone is like a figure 8. Other polar patterns are derived by creating a capsule that combines these two effects in different ways. The cardioid, for instance, features a partially closed backside, so its response is a combination of pressure and pressure gradient characteristics. Microphone polar patterns, microphone facing top of page and diagram, parallel to page. A microphone's directionality or polar pattern indicates how sensitive it is to sounds arriving at different angles about our central axis. The polar patterns illustrated above represent the locus of points that produce the same signal level outputs in the microphone if a given sound pressure level is generated from that point. How the physical body of the microphone is oriented relative to the diagrams depends on the microphone design. For large membrane microphones such as in the octaver, the upward direction in the polar diagram is usually perpendicular to the microphone body, commonly known as side fire, or side address. For small diaphragm microphones such as the Shure, It usually extends from the axis of the microphone, commonly known as end-fire, or top-end address. Some microphone designs combine several principles in creating the desired polar pattern. This ranges from shielding by the housing itself to electronically combining dual membranes. Omnidirectional. An omnidirectional microphone's response is generally considered to be a perfect sphere in 3 dimensions. In the real world, this is not the case. As with directional microphones, the polar pattern for an omnidirectional microphone is a function of frequency. The body of the microphone is not infinitely small and, as a consequence, it tends to get in its own way with respect to sounds arriving from the rear, causing a slight flattening of the polar response. This flattening increases as the diameter of the microphone reaches the wavelength of the frequency in question. Therefore, the smallest diameter microphone gives the best omnidirectional characteristics at high frequencies. The wavelength of sound at 10 kHz is little over an inch. The smallest measuring microphones are often 1/4 in diameter, which practically eliminates directionality even up to the highest frequencies. Omnidirectional microphones, unlike cardioids, do not employ resonant cavities as delays, and so can be considered the purest microphones in terms of low coloration. They add very little to the original sound. Being pressure sensitive, they can also have a very flat low-frequency response down to 20 Hz or below. Pressure-sensitive microphones also respond much less to wind noise and plosives than directional microphones. An example of a non-directional microphone is the round black 8-ball. Unidirectional. A unidirectional microphone is sensitive to sounds from only one direction. The diagram above illustrates a number of these patterns. The microphone faces upwards in each diagram. The sound intensity for a particular frequency is plotted for angles radially from 0 to 360 degree. Cardioid. The most common unidirectional microphone is a cardioid microphone, so named because the sensitivity pattern is a cardioid. The cardioid family of microphones are commonly used as vocal or speech microphones, since they are good at rejecting sounds from other directions. In 3 dimensions, the cardioid is shaped like an apple centered around the microphone, which is the stalk of the apple. The cardioid response reduces pickup from the side and rear, helping to avoid feedback from the monitors. Since pressure gradient transducer microphones are directional, putting them very close to the sound source results in a bass boost. This is known as the proximity effect. The SM58 has been the most commonly used microphone for live vocals for more than 40 years, demonstrating the importance and popularity of cardioid mix. A cardioid microphone is effectively a superposition of an omnidirectional and a figure-8 microphone. For sound waves coming from the back, the negative signal from the figure-8 cancels the positive signal from the omnidirectional element, whereas for sound waves coming from the front, the two add to each other. A hypercardioid microphone is similar, but with a slightly larger figure-8 contribution, leading to a tighter area of front sensitivity and a smaller lobe of rear sensitivity. A supercardioid microphone is similar to a hypercardioid, except there is more front pickup and less rear pickup. While any pattern between omni and figure-8 is possible by adjusting their mix, common definitions state that a hypercardioid is produced by combining them at a 3:1 ratio, producing nulls at 109.5 degree, while supercardioid is produced with a 5:3 ratio, with nulls at 126.9 degree. Bidirectional, figure-8, or bidirectional microphones receive sound equally from both the front and back of the element. Most ribbon microphones are of this pattern. In principle, they do not respond to sound pressure at all, only to the change in pressure between front and back. Since sound arriving from the side reaches front and back equally, there is no difference in pressure and therefore no sensitivity to sound from that direction. In more mathematical terms, while omnidirectional microphones are scalar transducers responding to pressure from any direction, bidirectional microphones are vector transducers responding to the gradient along an axis normal to the plane of the diaphragm. This also has the effect of inverting the output polarity for sounds arriving from the backside. Shotgun and parabolic microphones. Shotgun microphones are the most highly directional. Their directional pattern has a very narrow lobe in the forward direction and rejects sound from other directions. They have small lobes of sensitivity to the left, right, and rear but are significantly less sensitive to the side and rear than other directional microphones. This results from placing the element at the back end of a tube with slots cut along the side. Wave cancellation eliminates much of the off-axis sound. Due to the narrowness of their sensitivity area, shotgun microphones are commonly used on television and film sets, in stadiums, and for field recording of wildlife. Parabolic microphones have similar characteristics, but often have poorer bass response. Boundary or PZM. Several approaches have been developed for effectively using a microphone in less than ideal acoustic spaces, which often suffer from excessive reflections from one or more of the surfaces that make up the space. If the microphone is placed in, or very close to, one of these boundaries, the reflections from that surface are not sensed by the microphone. Initially this was done by placing an ordinary microphone adjacent to the surface, sometimes in a block of acoustically transparent foam. Sound engineers Ed Long and Ron Wickersham developed the concept of placing the diaphragm parallel to and facing the boundary. While the patent has expired, Pressure Zone Microphone and PZM are still active trademarks of Crown International, and the generic term boundary microphone is preferred. While a boundary microphone was initially implemented using an omnidirectional element, it is also possible to mount a directional microphone close enough to the surface to gain some of the benefits of this technique while retaining the directional properties of the element. Crown's trademark on this approach is phase coherent cardioid, or PCC, but there are other makers who employ this technique as well. Application-specific designs. A lavalier microphone is made for hands-free operation. These small microphones are worn on the body. Originally, they were held in place with a lanyard worn around the neck, but more often they are fastened to clothing with a clip, pin, tape or magnet. The lavalier cord may be hidden by clothes and either run to an RF transmitter in a pocket or clipped to a belt, or run directly to the mixer. A wireless microphone transmits the audio as a radio or optical signal rather than via a cable. It usually sends its signal using a small FM radio transmitter to a nearby receiver connected to the sound system, but it can also use infrared waves if the transmitter and receiver are within sight of each other. A contact microphone picks up vibrations directly from a solid surface or object, as opposed to sound vibrations carried through air. One use for this is to detect sounds of a very low level, such as those from small objects or insects. The microphone commonly consists of a magnetic transducer, contact plate and contact pin. The contact plate is placed directly on the vibrating part of a musical instrument or other surface, and the contact pin transfers vibrations to the coil. Contact microphones have been used to pick up the sound of a snail's heartbeat and the footsteps of ants. A portable version of this microphone has recently been developed. A throat microphone is a variant of the contact microphone that picks up speech directly from a person's throat, which it is strapped to. This lets the device be used in areas with ambient sounds that would otherwise make the speaker inaudible. A parabolic microphone uses a parabolic reflector to collect and focus sound waves onto a microphone receiver, in much the same way that a parabolic antenna does with radio waves. Typical uses of this microphone, which is unusually focused front sensitivity and can pick up sounds from many meters away, include nature recording, outdoor sporting events, eavesdropping, law enforcement, and even espionage. Parabolic microphones are not typically used for standard recording applications, because they tend to have poor low-frequency response as a side effect of their design. A stereo microphone integrates two microphones in one unit to produce a stereophonic signal. A stereo microphone is often used for broadcast applications or field recording where it would be impractical to configure two separate condenser microphones in a classic XY configuration for stereophonic recording. Some such microphones have an adjustable angle of coverage between the two channels. A noise-cancelling microphone is a highly directional design intended for noisy environments. One such use is in aircraft cockpits where they are normally installed as boom microphones on headsets. Another use is in live event support on loud concert stages for vocalists involved with live performances. Many noise-cancelling microphones combine signals received from two diaphragms that are in opposite electrical polarity or are processed electronically. In dual diaphragm designs, the main diaphragm is mounted closest to the intended source and the second is positioned farther away from the source so that it can pick up environmental sounds to be subtracted from the main diaphragm's signal. After the two signals have been combined, sounds other than the intended source are greatly reduced, substantially increasing intelligibility. Other noise-cancelling designs use one diaphragm that is affected by ports open to the sides and rear of the microphone, with the sum being a 16 dB rejection of sounds that are farther away. One noise-cancelling headset design using a single diaphragm has been used prominently by vocal artists such as Garth Brooks and Janet Jackson. A few noise-cancelling microphones are throat microphones. Connectors. The most common connectors used by microphones are, male XLR connector on professional microphones, a 1/4 inch phone connector on less expensive consumer microphones, using an unbalanced 1/4 inch TS phone connector. Harmonica microphones commonly use a high-impedance 1/4 inch TS connection to be run through guitar amplifiers. 3.5 ohm stereo mini phone plug on very inexpensive and computer microphones. Some microphones use other connectors, such as a 5-pin XLR, or mini XLR for connection to portable equipment. Some lavalier microphones use a proprietary connector for connection to a wireless transmitter, such as a radio pack. Since 2005, professional quality microphones with USB connections have begun to appear, designed for direct recording into computer-based software. Impedance matching. Microphones have an electrical characteristic called impedance, measured in ohmsa, copyright, that depends on the design. Typically, the rated impedance is stated. Low impedance is considered under 600 AI copyright. Medium impedance is considered between 600 AI copyright and 10 key copyright. High impedance is above 10 key copyright. Owing to their built-in amplifier, condenser microphones typically have an output impedance between 50 and 200 AI copyright. The output of a given microphone delivers the same power whether it is low or high impedance. If a microphone is made in high and low impedance versions, the high impedance version has a higher output voltage for a given sound pressure input, and is suitable for use with vacuum tube guitar amplifiers, for instance, which have a high input impedance and require a relatively high signal input voltage to overcome the tube's inherent noise. Most professional microphones are low impedance, about 200 AI copyright or lower. Professional vacuum tube sound equipment incorporates a transformer that steps up the impedance of the microphone circuit to the high impedance and voltage needed to drive the input tube. The impedance conversion inherently creates voltage gain as well. External matching transformers are also available that can be used in line between a low-impedance microphone and a high-impedance input. Low-impedance microphones are preferred over high-impedance for two reasons. One is that using a high-impedance microphone with a long cable results in high-frequency signal loss due to cable capacitance, which forms a low-pass filter with the microphone output's impedance. The other is that long high-impedance cables tend to pick up more hum as well. Nothing is damaged if the impedance between microphone and other equipment is mismatched. The worst that happens is a reduction in signal or change in frequency response. Most microphones are designed not to have their impedance matched by the load they are connected to. Doing so can alter their frequency response and cause distortion, especially at high sound pressure levels. Certain ribbon and dynamic microphones are exceptions, due to the designer's assumption of a certain load impedance being part of the internal electroacoustical damping circuit of the microphone. Digital microphone interface. The AES-42 standard, published by the Audio Engineering Society, defines a digital interface for microphones. Microphones conforming to this standard directly output a digital audio stream through an XLR or XLD male connector, rather than producing an analog output. Digital microphones may be used either with new equipment with appropriate input connections that conform to the AES-42 standard, or else via a suitable interface box. Studio-quality microphones that operate in accordance with the AES-42 standard are now available from a number of microphone manufacturers. Measurements and specifications. Because of differences in their construction, microphones have their own characteristic responses to sound. This difference in response produces non-uniform phase and frequency responses. In addition, microphones are not uniformly sensitive to sound pressure, and can accept differing levels without distorting. Although for scientific applications microphones with a more uniform response are desirable, this is often not the case for music recording, as the non-uniform response of a microphone can produce a desirable coloration of the sound. There is an international standard for microphone specifications, but few manufacturers adhere to it. As a result, comparison of published data from different manufacturers is difficult because different measurement techniques are used. The Microphone Data website has collated the technical specifications complete with pictures, response curves and technical data from the microphone manufacturers for every currently listed microphone, and even a few obsolete models, and showed the data for them all in one common format for ease of comparison. 3. Caution should be used in drawing any solid conclusions from this or any other published data, however, unless it is known that the manufacturer has supplied specifications in accordance with ʻmaɪk 60268-4. A frequency response diagram plots the microphone sensitivity in decibels over a range of frequencies, generally for perfectly on-axis sound. Frequency response may be less informatively stated textually like so: 30 Hz = 16 kHz plus or minus 3 a decibel. This is interpreted as meaning a nearly flat, linear, plot between the stated frequencies, with variations in amplitude of no more than plus or minus 3 decibels. However, one cannot determine from this information how smooth the variations are, nor in what parts of the spectrum they occur. Note that commonly made statements such as 20 Hz = 20 kHz are meaningless without a decibel measure of tolerance. Directional microphones' frequency response varies greatly with distance from the sound source, and with the geometry of the sound source. ʻmaɪk 60268-4 specifies that frequency response should be measured in plane progressive wave conditions, but this is seldom practical. Close-talking microphones may be measured with different sound sources and distances, but there is no standard and therefore no way to compare data from different models unless the measurement technique is described. The self-noise or equivalent noise level is the sound level that creates the same output voltage as the microphone does in the absence of sound. This represents the lowest point of the microphone's dynamic range, and is particularly important should you wish to record sounds that are quiet. The measure is often stated in decibel, A, which is the equivalent loudness of the noise on a decibel scale, frequency weighted for how the ear hears, for example, 15 dB/SPL. The lower the number the better. Some microphone manufacturers state the noise level using ITU or 468 noise weighting, which more accurately represents the way we hear noise, but gives a figure some 11 14 a decibel higher. A quiet microphone typically measures 20 dB/SPL or 32 decibel SPL 468 weighted. Very quiet microphones have existed for years for special applications, such the BRA 1/4 L and CJ 4179, with a noise level around 0 decibel SPL. Recently some microphones with low noise specifications have been introduced in the studio entertainment market, such as models from Neumann and Rada that advertise noise levels between 5 €7 a dB. Typically this is achieved by altering the frequency response of the capsule and electronics to result in lower noise within the A weighting curve, while broadband noise may be increased. The maximum SPL the microphone can accept is measured for particular values of total harmonic distortion, typically 0.5%. This amount of distortion is generally inaudible, so one can safely use the microphone at this SPL without harming the recording. Example: 142 decibel SPL peak. The higher the value, the better, although microphones with a very high maximum SPL also have a higher self-noise. The clipping level is an important indicator of maximum usable level, as the 1% of THD figure usually quoted under max SPL is really a very mild level of distortion, quite inaudible especially on brief high peaks. Clipping is much more audible. For some microphones the clipping level may be much higher than the max SPL. The dynamic range of a microphone is the difference in SPL between the noise floor and the maximum SPL. If stated on its own, for example 120 decibel, it conveys significantly less information than having the self-noise and maximum SPL figures individually. Sensitivity indicates how well the microphone converts acoustic pressure to output voltage. A high-sensitivity microphone creates more voltage and so needs less amplification at the mixer or recording device. This is a practical concern but is not directly an indication of the microphone's quality, and in fact the term sensitivity is something of a misnomer, transduction gain being perhaps more meaningful, because true sensitivity is generally set by the noise floor, and too much sensitivity in terms of output level compromises the clipping level. There are two common measures. The international standard is made in millivolts per Pascal at 1 kHz. A higher value indicates greater sensitivity. The older American method is referred to a 1 volt per Pascal standard and measured in plain decibels, resulting in a negative value. Again, a higher value indicates greater sensitivity, so a 60 decibel is more sensitive than a 70 decibel. Measurement microphones. Some microphones are intended for testing speakers, measuring noise levels and otherwise quantifying an acoustic experience. These are calibrated transducers and are usually supplied with a calibration certificate that states absolute sensitivity against frequency. The quality of measurement microphones is often referred to using the designations Class 1, Type 2 etc., which are references not to microphone specifications but to sound level meters. A more comprehensive standard for the description of measurement microphone performance was recently adopted. Measurement microphones are generally scalar sensors of pressure. They exhibit an omnidirectional response, limited only by the scattering profile of their physical dimensions. Sound intensity or sound power measurements require pressure gradient measurements, which are typically made using arrays of at least 2 microphones, or with hot wire anemometers. Microphone calibration. To take a scientific measurement with a microphone, its precise sensitivity must be known. Since this may change over the lifetime of the device, it is necessary to regularly calibrate measurement microphones. This service is offered by some microphone manufacturers and by independent certified testing labs. All microphone calibration is ultimately traceable to primary standards at a national measurement institute such as NPL in the UK, PTB in Germany and NIST in the United States, which most commonly calibrate using the reciprocity primary standard. Measurement microphones calibrated using this method can then be used to calibrate other microphones using comparison calibration techniques. Depending on the application, measurement microphones must be tested periodically and after any potentially damaging event, such as being dropped or exposed to sounds beyond the acceptable level. Microphone array and array microphones. A microphone array is any number of microphones operating in tandem. There are many applications, systems for extracting voice input from ambient noise, surround sound and related technologies, locating objects by sound, acoustic source localization, for example, military used to locate the source, of artillery fire. Aircraft location and tracking. High-fidelity original recordings, 3D spatial beamforming for localized acoustic detection of subcutaneous sounds. Typically, an array is made up of omnidirectional microphones distributed about the perimeter of a space, linked to a computer that records and interprets the results into a coherent form. Microphone windscreens. Windscreens are used to protect microphones that would otherwise be buffeted by wind or vocal plosives from consonants such as p, b, etc. Most microphones have an integral windscreen built around the microphone diaphragm. A screen of plastic, wire mesh or a metal cage is held at a distance from the microphone diaphragm, to shield it. This cage provides a first line of defense against the mechanical impact of objects or wind. Some microphones, such as the Shure SM58, may have an additional layer of foam inside the cage to further enhance the protective properties of the shield. One disadvantage of all windscreen types is that the microphone's high-frequency response is attenuated by a small amount, depending on the density of the protective layer. Beyond integral microphone windscreens, there are three broad classes of additional wind protection. Microphone covers. Microphone covers are often made of soft open-cell polyester or polyurethane foam because of the inexpensive, disposable nature of the foam. Optional windscreens are often available from the manufacturer and third parties. A visible example of an optional accessory windscreen is the A2WS from Shure, one of which is fitted over each of the two Shure SM57 microphones used on the United States President's lectern. One disadvantage of polyurethane foam microphone covers is that they can deteriorate over time. Windscreens also tend to collect dirt and moisture in their open cells and must be cleaned to prevent high-frequency loss, bad odor and unhealthy conditions for the person using the microphone. On the other hand, a major advantage of concert vocalist windscreens is that one can quickly change to a clean windscreen between uses, reducing the chance of transferring germs. Windscreens of various colors can be used to distinguish one microphone from another on a busy, active stage. Pop filters. Pop filters or pop screens are used in controlled studio environments to minimize plosives when recording. A typical pop filter is composed of one or more layers of acoustically transparent gauze-like material, such as woven nylon stretched over a circular frame and a clamp and a flexible mounting bracket to attach to the microphone stand. The pop shield is placed between the vocalist and the microphone. The closer a vocalist brings his or her lips to the microphone, the greater the requirement for a pop filter. Singers can be trained either to soften their plosives or direct the air blast away from the microphone, in which cases they do not need a pop filter. Pop filters also keep spittle off the microphone. Most condenser microphones can be damaged by spittle. Blimps. Blimps are large, hollow windscreens used to surround microphones for outdoor location audio, such as nature recording, electronic news gathering, and for film and video shoots. They can cut wind noise by as much as 25 decibel, especially low-frequency noise. The blimp is essentially a hollow cage or basket with acoustically transparent material stretched over the outer frame. The blimp works by creating a volume of still air around the microphone. The microphone is often further isolated from the blimp by an elastic suspension inside of the basket. This reduces wind vibrations and handling noise transmitted from the cage. To extend the range of wind speed conditions in which the blimp remains effective, many have the option of a secondary cover over the outer shell. This is usually an acoustically transparent, synthetic fur material with long, soft hairs. Common and slang names for this include dead cat, or wind muff. The hairs deaden the noise caused by the shock of wind hitting the blimp. A synthetic fur cover can reduce wind noise by an additional 10 decibel. See also: geophonia transducer for sound within the earth, hydrophonia transducer for sound in water, ionophonia plasma-based microphone, microphone connector, microphone practitioner examples of usage, nominal impedance, shock mounter microphone mount that suspends the microphone in elastic straps. Notes: a microphone windscreen is sometimes called a wind gag, or dead cat or yeti. References. External links, info, pictures and sound bites from vintage microphones, microphone sensitivity conversion decibel re 1 volt per Pascal and transfer factor megavolt per Pascal, searchable database of specs and component info from 1000 plus microphones, microphone construction and basic placement advice, history of the microphone, large versus small diaphragms in omnidirectional microphones, guide to condenser microphones, measurement engineering grade microphone basics,